Hello everyone, and thank you for joining us for today's Surface Measurement Systems online workshop. We're very lucky today to be collaborating on this workshop with the ASG Analytik-Service AG, Dr. Klaus Troisker, who has very kindly offered to take part and share some of his findings with us. Before we kick off with our first presentation, I'd like to remind everyone that we will have live Q&A sessions with our speakers today. And you can take part in these in one of two ways. You can submit your question in writing in the Writings tab, or alternatively, you can raise your hand when we get to the question section, and I can unmute your microphone and you can ask the question audibly over the mic. This is more suitable for maybe some long form questions or questions where you may have a follow-up and want to have a bit more of a back and forth with the speaker. So please do take a moment to familiarize yourself with the webinar control panel, and so you can take part in the question and answer section later. Our first speaker today is Thomas Schmidt of Surface Measurement Systems, who will just be giving us a brief background on the instruments and science used to generate the results and findings we're going to be exploring here today. So without further ado, I will hand over to Thomas.
Yes, thank you, John. I'm Thomas, sales manager here in Germany, Switzerland, and Austria for Surface Measurement Systems. I am pleased that we are hosted today at the ASG Analytik-Service. Just for information, all the people invited chose or decided to go online. So that's the reason why we are in office. Yeah, it looks like that is a past pandemic trend, that is just for information. I hope you can see my screen, John.
Yes, all good, Thomas.
Okay, thank you. Yeah, so I will start with that short introduction of, for those who don't know, Surface Measurement Systems, where we are coming from and what we are doing, and what are the collaboration with our customers. I try or start with that short introduction. Yeah, so Surface Measurement Systems, we have expertise. We are an expertise company. Founded by Professor Darrell Williams at Imperial College in London. So, and that in 1990. So we are a scientific company and have still a very scientific focus. And have today 2022 5 subsidiaries, different partners and distributors, 2 manufacturing sites, and around 100 people. So Surface Measurement Systems started really in 1990-91 with a dynamic vapor absorption. That was the first commercial system, analytic system for water absorption and a gravimetric analyzer. And that was delivered on request, first system to Pfizer. Simply at that time, there was a really need to get more accurate instrument to measure absorption and absorption kinetics and automated instruments. And that was the first instrument who were sold at this time. And today, there are around 2,000 units sold worldwide, more than 2,000, let's say. So we try really with our system to expand the frontiers of particles and materials, and we are very known expert in developing systems for characterization of solid state materials and liquids, and in many ways a pioneer for many systems. And and that's where we are good, where we are excellent. It is in producing that innovative systems for our customer, for you, and for research and department as quality control. Here's the map, a little of yeah, where we are. So the headquarter is in London for instruments and contract laboratories, but we have other side subsidiaries, and you see from the picture where it's manufacturing, where we have labs, where we have regional support. So support is given worldwide, and we are selling our instrument from, I would say, Australia over Asia, Europe, and of course the US also, which are important locations. Yeah, and I will give you at the end of the presentation some contacts if you would like to join your local distributor where you are in the world. That I will give at the end of the presentation. Yeah, the instrument is an important part of the business. Yeah, and of course we are manufacturing, producing the system with quality control, but also we have a big department, R&D, science, and science department to do the science, of course, but also to develop that systems, and also software development. Software development is still or is in-house at Surface Measurement Systems. Yeah, to have a perfect software to control, of course, the instrument, but also to analyze the samples. Laboratories and scientific support, that's what we can provide you. The technical support, of course, and service. And internally, we have other department, human resources, finance, and of course also as a link to you, sales and marketing and business development. So what you see here on that screen is the dynamic vapor sorption instrument. That at the schematic you see that's a balance, that's dual balance. And what you make in short is to measure the uptake and loss of moisture, organic vapors, or gases, but also of mixtures. Yeah, if you think, for example, about carbon capture, you would like to know about CO2 adsorption in presence of humidity. Just to give an example, we have a surface energy analyzer. That's more to measure surface, to characterize surface and to measure surface energy of solid materials, powders, particles, fibers, but also films and plates. And that's based on gas chromatography, just its inverse gas chromatography. You use probe molecules, I would say, to probe and to characterize the surface of different materials. Last but not least, and we will see more later with Paul, that's a vapor pressure analyzer. Yeah, the vapor pressure analyzer to make the measurements of the vapor pressure of liquids and solids. So that's the system and the measurements where Paul will tell you much more. Yeah, so DVS, you see here, I would say, a range of DVS instruments. So that is depending, I would say, on the vapors you are using. If you're using water vapor, organic vapors, if you're doing gas capture, you have a different system who work at different conditions. You can go to high temperature, you can go to low temperature. You can also add some analysis as a video camera. It's like a small video microscope, or you can measure also during the sorption process of a Raman or air structure changes. Yeah, so that is for dynamic vapor sorption, gravimetric dynamic vapor sorption. And here you see the IGC. Just go shortly through, just that you have heard that you can measure with that the dispersive and solar and polar surface energies, yeah, the heat and entropy of sorption. Acid base sites and interaction. You can measure on multiple solid material BT specific surface area. You can measure phase transition. In this case, they are more, I would say, a surface phase transition. You can see with inverse gas chromatography. And when you go in the material, you can measure also solubility parameters of materials, especially of solid materials and composites. And of course, when measuring the surface energy, you can rely it and measure or calculate the work of cohesion and adhesion between different materials. And here, in short, the vapor pressure analyzer. So all materials enter or solid materials phase by sublimation or evaporation when it's going from a liquid to a gas. And the vapor pressure of a material at thermodynamic equilibrium is a very important property of the material or of the liquid, and that in function of temperature. And as we'll see, we are following the OECD guideline and using Knudsen method. As I say, more later. Yeah. And the second part of our business is contract measurements and expertise in contract laboratories. Yeah. For that, we decided during the pandemic time to open a new lab. Yeah, because we have different labs, they did different contract analysis, but now for at least for solid samples, we opened a new lab in India. It has a surface of 6,000 square meters with different instruments for solid and particle material characterization. Yeah. And when you are going to fuse, to liquid fuse, you can go also, of course, to partners. And this we have partnership with ASG Analytik-Service, where the workshop today is. So, and we will see from Klaus a presentation about the analytics done there. So it is perfect for measuring fuels and different liquid fuels here in Germany. So I will end with thank you, and the stage is open for one or two questions. If you have question in Germany, we are in Heidelberg, surface measurements Germany. Of course, the other part of the world are United Kingdom, North America, and India. And if you have any question about who is your partner in your country, don't hesitate to contact us, and we will give you the local or partner who is supporting you and responsible for you. Yeah, thank you for your attention. The stage is open for a question if there is a question. Thank you.
Okay. If we have no questions, we'll jump ahead to Dr. Troiska's presentation.
Yeah. So please.
Thank you very much, Thomas.
Okay. Thanks.
Thank you. So next up, we have Dr. Klaus Troiska from the ASG Analytik-Service AG to tell us a bit more about the work they do and share some of his findings with us. A massive thank you to Klaus for being with us here today. So without further ado, I will hand over. Remember, we will be having a Q&A session at the end of this presentation. So at any point, if you have a query, please submit it in the questions panel, and I will ask Klaus at the end. Thank you.
Can you see the presentation now?
Yes, Klaus, we can see it.
Yes, yes.
I'm not in presentation mode.
But we just, that's perfect, yeah.
now is it fine?
That's perfect, Klaus, yes.
Yes. So I want to welcome you all to this presentation and this webcon. And what you can see here is where we located. Usually we planned to invite you to come to us, but now we only can show you the picture where we are located. So some further data on our company. We were founded in 1992, so 2 years later than the other company. We are located in Neuses, Germany, which is near Augsburg, or for the ones who are further, it's near Munich, which is well known. We have a turnover of about 5 million euro, and up to now we have 55 employees. Some data about the history of our company. As already said, founded in 1992. The first accreditation was in 1998 by the former Dasmin. Then in 2003, we constructed our own laboratory building. Before we rented some rooms, and of course this was soon too small, so the building was expanded, and laboratory space was larger, and we were able to install a mini plant lab. In 2015, we had the possibility to set up process engineering and widen the mini plant lab. In 2021, we had the conversion of the business ownership from the German GmbH to AG, which means it's shareholder owned. And last year, we began again to build a complex for new business. So let's have a closer look to the different segments of the ASG's business. So our most important part, of course, is analytics, because we are a commercial laboratory for fuels, especially, and we set up the mini plant lab since 2006. Furthermore, you are able to buy some products, some fuels which are specially designed on your wishes, because on the filling station you can only buy typical fuels, but if you want to experiment with future fuels or test your parts, what they can support, then you can order from 1 liter to 1,000 liter of a special fuel. Furthermore, there is the possibility to use our product development. We are able to develop some machines which are customer designed. Our analytics, a little in more detail, to give you an overview. We run about more than 700 analytical methods, and 157 thereof are accredited analytical methods. More in detail, the techniques we are applying For the metals, it's mainly ICP OES, and for lower concentrations, we can use the ICP mass spectrometry, and furthermore the X-ray techniques for seeing the metals. Another point is distillation, recording distillation curves and cold flow properties of fuels by freezing point, cloud point, pour point, and cold filter plugging point, which is, of course, important for the colder regions of Europe. Another point is thermal stability properties and corrosion properties, which can be measured by different techniques. Furthermore, of course, we have the possibility to do titrations, acids or water or whatever, lubricity measurements, or measurement of elemental analysis, carbon, hydrogen, nitrogen, oxygen, and sulfur, of course. Additionally, we can do some measurements on viscosity, density, photometry, FTIR measurements, which are mostly physical properties. And of course, fuel is organic liquid. The most powerful instrument to analyze organic molecules is gas chromatography. We have combined the gas chromatography with the different detectors, which are the common FID, mass spectrometer, and we can also enhance the chromatographic separation by GC times GC, combined with a time of flight mass spectrometer, or another detector, which VOV, vacuum ultraviolet light. And of course, for not so volatile molecules, we can use HPLC, which is high performance liquid chromatography. Some words about the mini plant. Now, mini plant, we can run different types of distillation because we are running different columns, different packing elements, centric tube columns. We can run them in continuously way or in batch wise. We can also apply different reactors. They can be made of glass or for higher pressures, autoclaves, tubular reactors, batch reactors, or special reactors for hydrogenation. And additionally, we deal with process engineering. We have the possibility of model validation, modeling, design of experiments as well. This gives us the chance to participate in funded research projects like ILCOCON, which is an infrared system which analyzes what goes on in a column. The DME plus X project means that drop-in fuels containing DME as renewable component are investigated. A further project deals with hydrogenation of squalene to squalane, and this should apply microemulsions. Furthermore, a very important subject is to produce sustainable aviation fuels from methanol, and there we can participate in 2 different projects. And we mostly do the analytical part, which is necessary for characterizing the products. Furthermore, we offer products for the biodiesel industry, which is a C19 methyl ester, or reference materials, quality check materials, and as already mentioned, specially designed gasoline and diesel fuels, and very specialty is the OME and synthetic fuels on demand. Biodiesel, of course, we also offer several types of biodiesel and mixtures, also for round robin use. So next part is the product development, which we are running. For instance, the macro thermomechanic analyzer, which was designed for measurement of foams. When foams are made from heating a liquid, then you can measure with this device how much foam is produced. The next one was a quite long development. It's the AFIDA, Advanced Fuel Ignition Delay Analyzer, and this was designed for the measurement of cetane numbers, and it works that you inject the fuel in a heated chamber, and you measure the time from injection to pressure rises. And this time, this delay can be transferred into a cetane number. And these are only 2 examples. We also designed special reactors and high pressure density devices, which I can show you here. This is on the left side. You see the high pressure density device, and another one is for measuring lubricity according to HFRR, which means high frequency reciprocating rig. And we can have a look more detail. The high pressure measurement principle is like this. Special pumps generate pressure. I can show you here. These are the pumps which generate a pressure up to 2,400 bar. And in this cell, we can do a digital density measurement using the oscillating U-tube principle. And because of the high pressures, we have to use, of course, a stainless steel capillary. What you see here is the control unit and the thermostat for producing correct temperature for the density measurement. Another one which I mentioned before was the HFRR. The principle of this technique is an excenter, which you can see here on the scheme, oscillates with 50 Hertz, and inside here there is a ball that slides over a plate under certain pressure. The pressure is done by this metal plate, which is works gravimetrically in the end. A drop of your sample is put between the ball and the plate, and after a certain time, dimensions of the calotte is measured by a microscope. This is the normal technique of HFRR, and to use this for liquids having a high vapor pressure, we put all the system in such a housing which can be set under pressure, and so you can avoid evaporation of your sample during the measurement. And these are the schemes, but we can also have a view from above. This is the center which I showed you, and this is the chamber which can be set under pressure, and here will be located the ball and plate which does the measurement. And of course we have an electric control module for this device as well. So thank you for your attention, and please don't hesitate to contact me if there are any questions. And now the floor is open for your questions.
Thank you, Klaus. And yes, just to remind everyone, you can submit your question in writing, or you could raise your hand if you have a question you'd like to ask over the mic. So we'll just give everyone a minute or two to submit those. So a question here, Klaus. Is blue ammonia becoming a topic for ASG?
Yes. Yes, of course, ammonia is a gas under normal conditions, and you can only measure the lubricity under pressure, of course, or by cooling down. So this could be a candidate, and I have to ask my colleague. I'm not sure if the device is able to support the corrosive properties of it. Can ruin such a device, and I have to ask my colleague if this is possible. So this was not yet tested, and it is more designed for methanol, which has a high vapor pressure, but it's liquid. And you can use LPG for the measurement of lubricity.
Thank you. We have another question here asking, regarding the vapor pressure on the high frequency testing rig, what are the maximum possible vapor pressures of the oils you used?
It's about 10 bar.
Thank you. Yeah, I think that's all the questions submitted for now. So once again, Klaus, thank you so much for being here today to share with us ASG's work. We really appreciate it.
You're welcome.
So without further ado, we'll now go to our final presentation of the day. And this is going to be presented by Dr. Paul Giacomi, who will be sharing some of the findings from the work at Surface Measurement Systems. So without further ado, I'll hand over to Paul. Please do remember, we will be having a Q&A session at the end of Paul's presentation. So remember to jot down any questions you have as the presentation progresses. So over to you, Paul.
John for the introduction. Hello, everyone. Just double check if you can see my screen.
Yes, we can.
Great. Okay, well, I'm very happy to have the chance to speak at this exciting hybrid event organized by Surface Measurement Systems in partnership with ASG Analytik. And today we'll go on a short journey to better understand and measure a humble property with a big impact, as we also glean from Dr. Troster's presentation, vapor pressure. We'll see that it's something that we often take for granted, while in reality it's a little bit more subtle. And we'll start with a short outline of the talk. We have a short intro to vapor pressure of a substance, how it's being assessed on different types of materials, fluids, solids, and a little bit of detail of two particular methods used to assess vapor pressure, the Knudsen diffusion method and the static method, with examples of each. So this is the most common way you encounter vapor pressure in daily life, and provides an intuitive understanding of vapor pressures, where you have a heated saucepan filled with water with a lid on top, and you leave it on the hob for a while, and the lid flies off because of the accumulation of steam and vapor as the temperature increases. So heating up of a substance creates a gaseous phase, the population of molecules in the vapor phase above that liquid, and that is translated to a pressure, which we call the vapor pressure of, in this case, a liquid. Throughout the presentation, you'll see vapor pressure abbreviated either as PV or sometimes P naught. The underlying mechanism behind vapor pressure is quite straightforward. As temperature increases, so does the vibrational motion of molecules. So molecules start vibrating faster and faster. And when there's an open interface between a liquid or a solid and an empty vacuum or a bottle, every so often a molecule has enough energy to overcome the liquid-liquid interactions and fly into the gas phase. This process is reversible, so a molecule in the gas phase can go back into the liquid phase if it just flies into the liquid. So at one point, there is an equilibrium being attained, where there's an equal number of molecules going into the gas phase and an equal number of molecules going into the liquid phase. That equilibrium pressure is called the vapor pressure, which is now measured inside this container. There's only the influence of temperature. In general, not many other variables can have an influence. And from a purely thermodynamic point of view, only temperature has an influence on vapor pressure. And it's important to note that every substance essentially has a vapor pressure. And we have over here in the table a couple of examples of different substances with different vapor pressures, starting from some of the lowest vapor pressures, which can be measured in 10 to the minus 13 bar. Glycerol, mercury, tungsten also has a vapor pressure at extremely high temperatures, so even pure elements like metals. And then we go to more familiar water, some freons, some gases, and some solvents, which start having higher and higher vapor pressures. So for example, carbon dioxide at 20 C has a 57 bar as its vapor pressure. So it's really something that can span a large magnitude of pressures. Let's take a look at how vapor pressure changes in the landscape of a substance. What we have here is the phase diagram, in this case the phase diagram of water, which allows us to discover the relationship between temperature and pressure. What we're going to do is we're going to walk the minimum pressure equilibrium line on this phase diagram, which means that there is the only pressure increase is due to the equilibrium. If we start over here, we look at the range of temperatures that we encounter in a daily life. So we see that at 100 Celsius, the vapor pressure of water is 101 kilopascal, which is an atmospheric pressure, which means that water boils at 101 kilopascals. But we can see that there's vapor pressures increasing logarithmically and decreasing logarithmically as we increase in pressure, until even if we decrease in pressure after the triple point, the equilibrium happens not between liquid water and water vapor, but between ice and vapor. So this is called sublimation, and it means that even solids have a vapor pressure which cannot be extrapolated from the liquid vapor pressure. This complete landscape is not easy to generate or to predict due to pressure values involved, starting from thousands of bar to 10 to the minus 11 bar. And something that also introduces a lot of complexity is the vapor pressure of mixtures. We can think of a mixture of two liquids, A and B, and intuitively one might say that the vapor pressure of a mixture of two compounds is a linear contribution between the vapor pressure of A and the vapor pressure of B. But this is not the case, as non-ideal effects can have significant deviations from this line. So one might find a vapor pressure curve as the mixture ratio increases, something along the lines of this, lower than the ideal or even higher than the ideal. It is very difficult to predict due to the complex thermodynamics involved. Here are some real-world examples of some bit more subtle mixtures, where we might not realize that there's mixtures of two compounds, so salt solutions and gas solubility. And we know for sure that dissolution of salts within water has an impact on the relative humidity, so on the vapor pressure of water, and we even use these as calibration standards. And similarly, the dissolution of atmospheric gas, for example, nitrogen or oxygen inside a fluid, can also similarly impact its vapor pressure. So vapor pressure is a variable that generally must be measured. A quick recap. Vapor pressure is a property that defines the amount of vapor a material generates at its surfaces. It can be produced both by solids through sublimation or evaporation, so it is applicable to both phases. And it's a function of temperature. Why would we want to know vapor pressure? Well, it's very important first for regulatory information, to understand the volatility of potentially toxic and dangerous compounds like pesticides, fertilizers, some pharmaceutical compounds. And it is generally required by the EPA and the ECH, but also to understand the process side, to understand the way, for example, oils volatilize or solvents volatilize inside the process. So it is generally a base material property, but it is desirable and required in many applications. Here are a couple of methods that are recognized can be used to measure vapor pressure by the OECD guidelines for the testing of chemicals. And you can see that different methods are applicable in different pressure ranges. And the two ones we're going to look at today are the Knudsen diffusion method and the static method. One which is applicable to low vapor pressures, so generally recommended 10 to the minus 10 to 1 Pascal, and the static method is applicable to higher pressures. Start with Knudsen infusion method. In this method, the sample is placed inside an enclosed cell with an orifice of a known dimension and placed into a vacuum. What will happen is inside the sample there will be a vapor pressure generated. Inside the cell there will be a vapor pressure generated by the sample, which will leave the cell through this small hole. And the rate at which this mass loss occurs is constant at a constant temperature because of the difference in pressure between the inside and the outside of the cell. So if this mass loss can be measured, it can be converted into a vapor pressure. And we see here how mass decreases as a function of time until it stabilizes as the entire compound inside the cell is lost. And often the way to do that is by using a sensitive microbalance to hold the cell with the compound together. And we'll go into a bit of detail further in the presentation. Once we have this gradient as a function of time, we need a couple of variables from which we can relate the rate of change in mass to the pressure. So we need the molecular weight of the material. We need the temperature at which the measurement was made, and we need to know the area of the orifice. Once we have all of these variables, we can relate the rate of mass loss, so the gradient of this line, to vapor pressure. And if we want to extrapolate vapor pressure at different temperatures, what we can do is we can use the integrated Clausius-Clapeyron equation, which relates one vapor pressure to the enthalpy of sublimation. So looking at this equation, if we have multiple vapor pressures measured at different temperatures, we can plot the logarithm of the vapor pressure as a function of the inverse of temperature. And the gradient of this line is related to the enthalpy of sublimation. So we can calculate the enthalpy of sublimation or vaporization in the case of a liquid and back calculate the vapor pressure at different temperatures by either extrapolating or filling in the blanks between experiments. This is how such an experiment looks on paper. What we see here is the temperature on one side and the mass measured in a Knudsen diffusion cell on the other. You see the temperature is increasing stepwise from 25 degrees to 70. And we see the rate of the mass loss. And for each step here, there is a different rate of mass loss, which corresponds to a different vapor pressure. So for each step of vapor pressure is calculated, the vapor pressure at 25, 30, at 40, etc. And then afterwards, using the Clausius-Clapeyron equation from the previous slide, the logarithm of pressure is plotted in the inverse of temperature. And we see a very good straight line fit, which allows us to calculate the enthalpy of sublimation. This material is benzoic acid, so this is a solid with a relatively high vapor pressure. But many other solids can be measured using different temperatures. These are measured with the surface measurement system vapor pressure analyzer, which combines a Knudsen diffusion cell. So this is a photo of exactly the setup as being used, with a small closed cup and an orifice making up the Knudsen diffusion cell, everything placed inside a very sensitive microbalance. The entire system is connected to a vacuum system, so a vacuum is pulled. And then there are two ways of controlling temperature, either by controlling the temperature of the entire enclosure, which can go from 10 to 70 C, or by using a local heating, which can go up to 400 C. So the total experimental temperature range is 10 to 400 Celsius. There's a base vacuum of 1 to 10 to the minus 6 torr attained inside the entire system. And all measurements are being done, the mass measurements are being done with the SMS Ultra Balance, which has an extremely high resolution of less than 1 micron. The Knudsen diffusion method was mentioned before, that is approved by the OECD, was on the previous table. This is how the schematic of the vapor pressure analyzer looks like. This is the actual instrument, which the Knudsen cell is in the sample side here. There is also a reference side to make sure that the sample is exposed to the same atmosphere, all connected to a vacuum system, and microbalance, the highly sensitive microbalance is in the top hat here. And this is the temperature controlled enclosure. This is the preheater, local heating, and everything is controlled by a PC with automatic software for control and for analysis to set up these incremental temperature steps, and then to analyze and get both the vapor pressure and the enthalpy of vaporization or of sublimation. We've seen this experiment before, but just a reminder of how the equipment takes the data out. This is data from the VPA, from the SMS vapor pressure analyzer. And now we're going to go into a little bit about how this calibration is being done with benzoic acid. This is one experiment, but here are actual data points from multiple experiments. This is the mass loss rate, the vapor pressure at each temperature, and a repeat to see the kind of repeatability that we get using this method. There's a back calculation of the orifice size, and this data is in very good agreement with previously published literature data. Similarly, for higher pressures, we can also do a calibration with naphthalene, which has a vapor pressure of 11 Pascal at 25 C. Good correspondence with the EPA value of 11.6 Pascal. So now we're going to go into a couple of case studies of the Knudsen diffusion method. It's just a few data points with various applications. So pesticides and fungicides, as mentioned, were important products to know the vapor pressure of, to measure toxicity, to conform to regulatory pressures. These are the vapor pressures measured from 4 different pesticides at 20, 25, and 20 C. We can see that they are extremely small, 10 to the -4, 10 to the -6, 10 to the -10 Pascal. They were successfully measured with the Knudsen diffusion method, which are also in good correspondence to literature. So these 25 C measurements were back extrapolated by using the enthalpy of vaporization determined at different temperatures. A more pertinent study, the vapor pressure of some lubricating oils, where the vapor pressure of certain lubricating oils with relatively low vapor pressures was measured. So these are some experiments, also see a good fit to the Kalashnikov line with vapor pressures around 13 millipascal. This is one oil here called oil A and oil C, with a pressure even lower, around 4 to 5 millipascals. Some data from silicone sealants, also important industrial compounds. So polymethyl siloxane was measured in vapor pressure in the range of 3 to 8 pascals. A couple of other examples. Triisopropylamine, tertiary amine, then caffeine, the vapor pressure of caffeine, of different forms of caffeine, was measured. And from there, they was able to look at the stability of the different forms. Ibuprofen, so pharmaceutical compounds, and red, orange, yellow polymorphs, which are compounds with a wide degree of polymorphicity. And there was a vapor pressure measured of the two polymorphs, or two polymorphs, the red and the orange polymorph, showing different vapor pressures, meaning that there are different interactions between the molecules of the two crystals, even though composed of the same molecules. Now we're going to go into the static method of vapor pressure measurement, which is generally applicable to higher pressures, to higher vapor pressures. It was mentioned before that if a liquid or a solid is placed inside a vacuum container, after some time, the equilibration between the molecules going into the atmosphere and from the gas phase into the liquid occurs. If we had a pressure gauge connected to the container, what we'd see is a condensation, an evaporation and condensation rate converging as pressure is increasing until it stabilizes to the vapor pressure of the liquid or of the solid. So the setup in which static vapor pressure is being measured looks a little bit like this, where we have a number of samples that are connected to a common line with a number of pressure sensors that have different accuracies and are applicable for different ranges from 10 to 10,000 to 1,000 torr, maximum measurable pressure. There's a vacuum pump that pulls a vacuum onto one sample at a time. The valve is then closed and the pressure is measured statically until equilibrium is achieved. And then the system is evacuated and the next sample can be tested. This is how the setup looks, and these are two samples that are connected to a common line going forward over here. And a couple of examples of lubricating oil vapor pressures using these static measurements. So a couple of solvents. We've got cyclohexane. We got here the sample is being introduced to the vacuum. We see pressure is increasing until it stabilizes at around 98 torr. Same with an octane. Equilibration is relatively fast at around 32 torr. And this is at 40 C. Cyclopentane at 38 Celsius, the much higher vapor pressure, 511 torr, and a more heavy compound, fluorocarbon perfluorodecaline at 25 C has a vapor pressure at 27 torr. The vapor pressures of mixtures can also be very simply measured through the static method. And we see here two samples, actually the samples that were in the photo before, of different molecular weight mixtures of different oligomers, all measured at 50 C. And we can see the two vapor pressures. So this is when sample 1 is measured, then everything is vacuumed, and sample 2 has been measured. So it is a very straightforward way of measuring vapor pressure, which is complementary to the Knudsen diffusion method. And to conclude, we had a short intro of vapor pressure of a substance and how to assess it. Hopefully you've seen that it's not a walk in the park on how to assess this important material property. And we've looked at two methods, the Knudsen diffusion method, using the SMS vapor pressure analyzer microbalance, and the static method using the SMS static vapor pressure analyzer, which are complementary methods which can obtain vapor pressures of both low vapor pressure substances like solids and high vapor pressure substances like fluids, for example, lubricating oils, solvents, etc., and mixtures as well. So I'd like to thank you for listening, and if there are any questions, I'm more than happy to answer.
Thank you, Paul. And yes, a reminder for our audience that if you would like to submit a question for Paul, please submit it in the questions panel, or you can raise your hand and we can unmute your microphone so you could ask your question. So we have our first question here, Paul. It asks, is it possible to connect EVA, MS or other?
Yes, there should be no problem to connect a mass spec. Yeah, it's just a case of connecting them at the outlet of the pump.
Thank you. We'll just give the attendees a moment to submit any questions. A question here. Does vapor pressure change when there is an inert gas involved?
In theory, no. If ideal gases are considered, the vapor pressure should not change. However, no gases are ideal. So if there is dissolution of the gas inside the vapor pressure can change because because liquid interactions can change. If the gas interacts with the particular vapor in the gas phase, there can also be changes of the vapor pressure through a different mechanism. So in an ideal case, no, but in reality, yes, in particular at high pressures of the gas phase.
Thank you. Someone has asked, can you give us an idea of the costs of contract measurements?
I believe Thomas is able to answer this question more than me, as he is more aware of the updated costs, perhaps.
Yeah. So I can give an idea, a level of costs, also depending, of course, on the temperature range. Yeah, you would like to measure, is it only one temperature or the full temperature range? But for a full measurement at each temperature, you have to count or think about 1,500, 1,800 euro, just to give an idea.
Thank you, Thomas. Can you measure with the static setup how long the time is to saturation would change when having an inert gas with any given pressure involved?
So if I understand it correctly, would the equilibration time change with an inert gas? It would, of course. The system can measure for very long times since it is vacuum tight. So generally, it's quite fast, a couple of minutes to a couple of hours, but we can measure up to days without much loss in pressure. Everything is completely leak tight. It's using swage law connections.
Yeah.
I hope that answers the question.
Yes, I hope that answers the question. If they have an extension, they could submit it, and we'll ask Paul for his thoughts. Let's give them a moment. Okay, it looks like that may be all of our questions. So, Paul, I would like to thank you. Oh, no, just one just cropped in there. Apologies. Have you done any measurements in this respect? I think related to the last question.
With an inert gas, I don't think we've we've done any of that, but we'd be open to exploring that for sure. If you can contact us, we can have a look. We can have a discussion of what your needs are. So of course we can explore it.
Great. And the best email address for that would be science@surfacemeasurementsystems.com. Is that correct?
Correct. Thank you, John.
Okay, I think that is now the last of our questions. So Thomas, would you like to add anything at the end before we wrap up for today?
Yes, I know from time to time some people don't ask questions in the meeting because of there are a lot of people in. So I would suggest if you have a question or you would like to measure a sample, to do a test or discuss an application with us, you can come back after the meeting to either science@surfacemeasurementsystems.com or info@surfacemeasurementsystems.com, or of course also to your local salesman or sales manager, and that possibility is open in all our application lab, and of course also for ASG Analytik-Service. If you have their requests, I will forward it to Klaus, or you can directly email Klaus for questions and requests. Yeah. Also, I would like to add, if there are other, I would say, workshop and webinars, please don't hesitate to go on our website www.surfacemeasurementsystems.com and have a look about the coming webinars. Perhaps there's a topic also of interest.
Thank you very much, Thomas, and another big thank you to all of our speakers today, and of course to you, the audience, for being with us to explore this topic. And a special thanks to Thomas for organising this educational event. Thank you again, Klaus, for joining us today.
Thank you, John. Thank you, Klaus. We see each other. Thank you, Paul. Yeah, and thank you also for all who take time and join that webinar, that meeting. Goodbye.
Thank you, everyone. Goodbye.